Okay, before we go to the exercise number 2 about hydrolysis modeling, I would like to introduce for you some basic concept or theory about the hydrolysis because it's very important for you to understanding the theory behind the simulation scenario rather than we just go to detail or very deep in the simulation model. So before we go with the video demonstration, I would like to briefly the basic and important theory for you about the residual chopping and hydrolytic modeling in SimGSM. So, the residual chopping, especially here, we're talking about the relative variability history. In this case, we talk about the relative permeability, and we know we have the core function of many rock and fluid descriptors, such as the wet ability, the low rate, and the interfacial tension, and also the saturation history profile, or hydrolytic. So, we know the relative history did yield for the modeling the effect of the CO2 chopping as the residual gas, and it is very important to include the effect in our simulation. So we know the relative permeability we should consider because that shows the function between rock and fluid, and also this account for the reduction in low and driven phase due to mutual interaction of different allowing phase. In general terms of relative rarity of a driven phase is a function of phase saturation. As you know, we have already defined in our model, but it can be in a function of many of rock and fluid descriptors. Typically, we study effect of various type recovery process in oil and gas reservoir, notably with the chemical or low salinity water loading. I will want to focus on last process the dependent of relative permeability on saturation history, which is most commonly known as the hydrolysis of the relative permeability curves. So, as we ingest our C2, this gas will most possibly follow in both the relative permeability the Rennes curve. Okay? With the curve we already defined in our symbol CCS in the base case scenario model. By the way of convection current, the C2 will start to migrate upward, as we already noted by the result were modeled by the way of gravity differential. This will result into initial degree of water saturation, especially in the proximity of the injection well, and followed by the subsequent degree of water saturation as the CO2 volume move away. So when the water saturation increase, the back followed by the class will change from the rennet to emission. As predicted by the hydrolysis model, so hydrolysis leads to a gap, in this case CO2 chopping, due to a shift of the residual gas saturation from the rennet to emission, and this process is thought is supposed to be contributed a lot to reduce the risk of the further migration of CO2 and let a ration of injected volume of CO2 toward the upper layer. We can enhance the containment of the gas into saline aquifer. Okay, so A myelination, the relative permeability characteristic, very important for the residual rat chopping evaluation. So regarding the modeling these effects, especially for two-phase system, like in our recent case, we need to have so that the ingredient for this to work about Greenwich curve with either input energy to our model. A selection of chopping model with associated parameter, typical parameter of the clean parameter. The length parameter is very common in the modeling of heterogeneous effects. So, in the exam manual, go into detail of the possible heterogeneous model. Available in the simulated exam had two phases, where the three-phase heterogeneous also include. And the common approach is based on the Carson and Land, based on the Larson and Cow model. But also for the G-phase, which is applicable to other simulation scenarios, like water alternating gas set. The water alternating gas set will be introduced for you in the event session. In that session, I will briefly introduce how water alternating gas enhance the CO2 trapping efficiency in terms residual and solubility trapping. Don't worry, I will introduce for you about this mechanism later on. And I would like to emphasize in REM model we consider the SIYS for the basic theory in heterogeneous. You can go to REM manual for further explanation about this effect. So now let's have a look at how heterogeneous model work in practice. On this restrictive loss of gas, relative permeability with gas saturation. So the curve indicated in black here with either input of the relative permeability gas, okay, defined user is automatically used by the simulator, a range curve. So in our model, we just run this is the only curve that simulator can use, because it only this curve and there no history yet applied. So that is the curve corresponding to the point of the reaching water saturation. When we input the gas in the red star to move upward, and before doing that we display some water, and water saturation will decrease. And so the gas saturation increase in this box, okay? So in the land model, I would like to emphasize in the land model, okay? The user can input a value of maximum gas trapping, okay? Maximum gas trapping, indicated by the SGT, okay? You can see the SGT max in this plot, okay? This value of course contains between the saturation reticle and Y minus and 1 minus correct water saturation, okay, and Y minus connect water, okay. You can see that the matchup can define it in constraint, and in this simulation scenario on the SimGZM, you can use this keyword for indicate the matchup in model, okay. So they are only Pauli, but normally the value of SGT mass is like between 0.3 to 0.5. Okay, so this value is used by the land model to calculate the boundary imbibition curve, which will be this curve here, imbibition curve. Okay, the bounding imbibition and Kenny curve in the ring color. Okay, and the bounding drainage curve in the black color. And the assumption that SGT mass is the maximum job restoration, then any point where reversal of the water saturation occur when water starts to come back into block near the well. For example, at this point SGH, okay, you indicate on this plot the land model calculate the corresponding canons, the inhibition curve, where the history is a square with a small curve. Okay, with a very small curve. Here, with is characterized by its own specific value of residual gas saturation, which is indicated in SGRS, which may be greater than the input saturation reticle. So that's how this process will work at the point where reversal of water saturation happens. We track out a different curve from the drainage curve. This scanning inhibition, scanning inhibition curve, which is normally characterized by the larger value of residual gas saturation. So the formula here, you can see the formula here. To the right of this slide, taking from the GEM manual, indicate that the land model parameter can indicate the district land model. The parameter calculation, the land constant is over indicated by the C value. Okay, and then it is also indicated how SGRS calculate. This parameter is calculated as a function of the parameter of C. Okay, you should remember that. And this keyword can found easily in the GEM manual. I just extract from the GEM manual to introduce for you how the land chopping working in CMG GEM. And in this exercise, I will introduce for you 3 sub-exercises about the hydraulic modeling. Exercise 2A. Our purpose is illustrate the mechanism of residual CO2 gas trapping phase during the carbon dioxide sequestration. In this exercise, what will you learn? We will activate the hydraulic effect in GEM, and we consider the CO2 injection will take place along the drainage curve. A convection current setup. The carbon dioxide raise up the structure and water forms. And following that, the water saturation is read in the clock, and the relative permeability curve follow the imbibition curve without the hydraulic. Accordingly, some gas will be trapped in the water saline aquifer. Okay, that's all about exercise 2A. For exercise 2B, we comparing the result between the limited of VS in finite altitude aquifer. And in this exercise, we make the aquifer much larger than the previous exercise using the bore volume multiplier. We study the reservoir water and gas saturation with time, evaluate the gas density. That is the exercise 2B. And the last exercise, we will consider the acceleration of residual gas trapping. So, how the injection of water over injection of CO2 can lead to increased residual rat trapping due to the hydrolysis effect. What will you learn in this exercise? We will learn the water injector adding to the model at the start location, then C2 injector. Another time the water will move downward and the C2 will move upward by the virtual gravity effect, and more C2 can be trapped in the aquifer. And also we consider the different water injection rate will be tested in this exercise. And we will go to one by one the sub-exercise for you understanding how residual trapping performance in SimGSM. See you all of you guys in the video demonstration.